In 2007, physicist Katherine Freese at the University of Michigan published a paper proposing something that rewrites the timeline of cosmic history. She suggested that the first luminous objects in the universe were not stars as we know them. They were dark stars. Massive objects powered not by nuclear fusion, but by the annihilation of dark matter particles colliding in their cores. These objects would have been enormous. Hundreds of times more massive than the sun, millions of times brighter, and they would have burned for millions of years before collapsing into black holes, leaving no remnants, no descendants, no observable trace in the universe today. Except that in 2022, the James Webb Space Telescope detected 3 galaxies in the early universe that should not exist. They were too massive, too bright, too structured for objects forming less than 400 million. Years after the Big Bang, galaxies this large should take billions of years to assemble. But Webb found them fully formed when the universe was only 3% of its current age. And when astrophysicist Cosmin Illy at Colgate University analyzed Webb's spectroscopic data in December 2023, he found something that matched the predictions Katherine Freese had made 16 years earlier. The objects had the exact luminosity, the exact temperature distribution, and the exact spectral signatures that dark stars should produce. Which means the first objects in the universe might not have been powered by hydrogen fusion. They might have been powered by something we still do not understand: dark matter. The invisible substance that makes up 85% of the universe's mass. And if dark stars existed, they would have fundamentally altered how galaxies formed, how black holes grew, and how the cosmos evolved from the primordial darkness into the structure we observe today. And we never knew they were there until Webb looked deep enough. The first stars are not a mystery because we do not know when they formed. Cosmological models predict that stars began igniting approximately 100 to 200 million years after the Big Bang during an era called the Cosmic Dawn, when the universe cooled enough for hydrogen gas to collapse under gravity and reach the temperatures required for nuclear fusion. The mystery is what those stars were made of. The universe immediately after the Big Bang contained only hydrogen, helium, and trace amounts of lithium. No carbon, no oxygen, no iron, none of the heavy elements that exist in stars today. Those elements are forged inside stars through nuclear fusion and dispersed into space when stars explode as supernovae, which means the first stars formed from pristine gas, untouched by any previous generation of stellar evolution. Astronomers call these objects population 3 stars. They should have been fundamentally different from the Sun. Computer simulations by astrophysicist Volker Braun at the University of Texas predict that population 3 stars were massive, between 100 and 1,000 times the mass of the Sun, because pristine hydrogen gas is inefficient at cooling and fragmenting into smaller clumps. The first stars were giants, and they were short-lived. Massive stars burned through their fuel rapidly, exhausting their hydrogen in just a few million years before exploding as supernova or collapsing directly into black holes. The first stars should have lived fast, died young, and left behind chemical signatures, enriching the primordial gas with heavy elements that later generations of stars incorporated. But no population 3 star has ever been directly observed. Despite decades of searching with Hubble, ground-based telescopes, and now Webb, astronomers have not found a single confirmed example. The universe's first stars, if they existed as predicted, have vanished completely. Except that in 2007, Katherine Freese proposed an alternative. What if the first objects were not powered by nuclear fusion at all? What if they were powered by dark matter? Katherine Freese's idea began with a question. Dark matter particles are everywhere in the universe, pervading galaxies, galaxy clusters, and the space between them. And if dark matter consists of particles that can collide and annihilate, releasing energy, then the densest regions of the early universe, the cores of collapsing gas clouds, should have contained enormous concentrations of dark matter. When a cloud of hydrogen gas collapses under gravity, it heats up. But in the early universe, before the first stars formed, there was no source of heat except gravitational compression. The gas cooled as it radiated energy away, slowly contracting into denser and denser clumps. And at the centers of those clumps, dark matter particles would have accumulated. Trapped by the gravitational potential well created by the collapsing gas, Freese calculated that if dark matter consists of weakly interacting massive particles, or WIMPs as many theoretical models predict, then the particle density in the core of a collapsing cloud could become so high that WIMPs would begin colliding and annihilating at significant rates. Each annihilation would convert to dark matter particles into energy, releasing photons, neutrinos, and other particles, according to Einstein's equation. E equals mc. That energy would heat the gas. And if the annihilation rate was high enough, the heating would prevent the gas from collapsing further, creating a stable object supported not by nuclear fusion but by dark matter annihilation, dark star. Freese and her collaborators, physicists Paolo Gondolo and Douglas Spoliar, published their calculations in 2008, predicting that dark stars could grow to masses exceeding 1,000 solar masses and shine with luminosities millions of times greater than the Sun. They would be cooler than fusion-powered stars, with surface temperatures around 10,000 Kelvin compared to the Sun's 5,800 Kelvin, making them appear red or orange rather than yellow or white. And critically, dark stars would have no heavy elements in their spectra. No metals, no carbon or oxygen absorption lines. They would be composed entirely of hydrogen and helium, identical to the primordial gas from which they formed. This prediction created a testable hypothesis. If dark stars existed, they should be detectable at high redshifts in the earliest epochs of the universe, appearing as extremely bright metal-free objects that do not fit the characteristics of ordinary stars. But finding them required a telescope powerful enough to detect individual objects in galaxies forming less than 500 million years after the Big Bang. Hubble could not do it. The objects were too faint, too distant, too redshifted. Only Webb, with its 6.5-meter mirror and infrared sensitivity, had the capability to see them. And in 2022, Webb began its search. Why would the universe's first light sources be powered by invisible matter? Until now, this looked like a theoretical curiosity, a speculative model proposing an exotic type of object that might have existed briefly in the early universe before being replaced by ordinary stars. But it was not speculative. Because in July 2022, the James Webb Space Telescope captured its first deep field image, a region of sky near the galaxy cluster SMACSO 7-3. The image revealed thousands of galaxies, many at redshifts exceeding 7, corresponding to times less than 700 million years after the Big Bang, and 3 of those galaxies appeared anomalous. They were designated JADES G SC 1320, JADES GSC 120, and JADES GSC 110, cataloged by the JWST Advanced Deep Extragalactic Survey. Astronomer Brant Robertson at the University of California, Santa Cruz, led the spectroscopic follow-up observations and found that the galaxies had redshifts between 10.4 and 13.2. Placing them between 325 and 400 million years after the Big Bang, but their masses were impossible. Spectroscopic analysis revealed that these galaxies contained between 1 billion and 10 billion solar masses worth of stars. Galaxies this massive should take billions of years to assemble through the hierarchical merging of smaller structures. But the universe at redshift 13 was only 325 million years old. There had not been enough time. This is the hidden barrier. It's a realization that the James Webb Space Telescope is detecting galaxies that should not exist according to standard models of structure formation. The galaxies are too massive, too bright, too evolved for their age. And then in December 2023, physicist Cosmin Illy at Colgate University, working with Katherine Freese and astrophysicist Gillian Paulin, published an analysis suggesting that these objects might not be galaxies at all, might be individual dark stars. Illy reanalyzed Webb spectroscopic data and found that the emission from the 3 anomalous objects matched the predicted spectrum of dark stars almost perfectly. The temperature was consistent. The luminosity was consistent. And critically, the objects showed no evidence of heavy element absorption lines. No metals, no carbon, no oxygen, exactly as dark star theory predicts. If these objects are dark stars, then they are the largest stellar objects ever observed, hundreds of thousands of times more massive than the Sun, powered not by fusion but by the continuous annihilation of dark matter particles streaming into their cores from the surrounding halo. But the analysis faced immediate skepticism. Astronomer Emma Curtis Lake at the University of Hertfordshire, who led the JADES spectroscopic team, argued that the objects are more likely compact galaxies containing millions of ordinary population 3 stars, rather than single dark stars. The spectral features, she contended, could be explained by a dense stellar population with low metallicity. This created a scientific standoff. The data was consistent with both interpretations. Either the objects are dark stars, proving that dark matter annihilation powered the first luminous objects in the universe, or they are extremely compact galaxies, confirming that early structure formation was far more efficient than models predict. The resolution required additional observations, and in 2024, Webb conducted those observations. Why does every deep observation reveal objects that break our models? In March 2024, the James Webb Space Telescope obtained deeper spectroscopic data on JWC SZ1320, the most distant of the 3 candidate dark stars. The observation used Webb's NIRSpec instrument in high-resolution mode, allowing astronomers to detect individual spectral lines with unprecedented precision. Astronomer Guocho Sun at Northwestern University led the analysis and found something that neither the dark star hypothesis nor the compact galaxy hypothesis predicted. The object spectrum contained a faint emission line corresponding to ionized helium, specifically helium that had been stripped of both electrons, leaving only the nucleus. Doubly ionized helium requires extreme ultraviolet radiation to produce. With photon energies exceeding 54 electron volts, ordinary stars, even massive population 3 stars, do not produce enough high-energy photons to ionize helium to this degree. The radiation field must be extraordinarily hard, dominated by photons far more energetic than any stellar photosphere can emit. But dark matter annihilation produces exactly this kind of radiation. When WIMPs annihilate, they create showers of secondary particles, including high-energy photons capable of ionizing helium. Freese and her team had predicted this signature in their 2008 paper, suggesting that dark stars should be surrounded by nebulae of doubly ionized helium. Glowing shells created by the intense radiation from the dark matter annihilation core. Sun's detection matched the prediction. Helium emission was real, and it could not be easily explained by any conventional astrophysical process. But the observations still did not constitute definitive proof. Astronomer Daniel Scherer at the University of Geneva proposed an alternative explanation. He suggested that the helium emission could be produced by a population of extremely hot metal-free stars, remnants of the first stellar generation, radiating at temperatures exceeding 100,000 Kelvin. This remained theoretically possible. It required fine-tuning. The stars would need to be hotter than any observed population 3-star candidate. They would need to exist in numbers large enough to ionize the surrounding gas, and they would need to have formed in a compact enough region that Webb's instruments could not resolve them individually. The dark star hypothesis required no fine-tuning. It predicted exactly what was observed. And then, in September 2024, physicist Tracy Slottier at MIT published a study analyzing the energy output required to explain JHG's SC130's luminosity. She calculated that if the object is a dark star, the dark matter annihilation rate in its core must be approximately 1051 WIMPs per second, converting roughly 1/10 of a solar mass of dark matter into energy every million years. This rate is sustainable. Dark matter halos in the early universe were dense enough to supply this annihilation rate for tens of millions of years, allowing dark stars to shine far longer than massive fusion-powered stars, which exhaust their fuel in just a few million years. Slottier's models predicted that dark stars should eventually collapse once the dark matter supply is depleted, forming intermediate mass black holes ranging from 1,000 to 100,000 solar masses. These black holes would then serve as the seeds for the supermassive black holes observed in galaxy centers today, solving another cosmological mystery: how supermassive black holes grew to billions of solar masses in less than a billion years. This was the missing piece. Because observations of quasars at high redshift, luminous objects powered by supermassive black holes, have revealed that billions solar mass black holes existed when the universe was less than 700 million years old. Standard models of black hole growth, which assume black holes start from stellar remnants of 10 to 100 solar masses, cannot explain how they grew so large so quickly. But if dark stars collapse into 100,000 solar mass black holes, the growth time problem disappears. The seeds are already massive, and they only need to accrete for a few hundred million years to reach the billion solar mass range observed in early quasars. In 2007, Katherine Freese proposed that the first objects in the universe were not stars. She did not know she was predicting what the James Webb Space Telescope would find 15 years later. She thought she was exploring a theoretical possibility, a niche scenario that might have occurred briefly before ordinary stars took over. 17 years later, the evidence is mounting. Webb has detected objects that match dark star predictions. The luminosities match. The temperatures match. The spectral features match. And the helium ionization signature, the hardest prediction to explain through conventional astrophysics, has been observed. This does not mean dark stars are confirmed. Science does not work through single observations. It requires multiple independent confirmations, alternative hypotheses tested and ruled out, and a convergence of evidence so overwhelming that no other explanation survives. But the possibility is real. If dark stars existed, then the history of the universe is not what we thought. The first light in the cosmos was not fusion, it was annihilation. The invisible substance that dominates the universe's mass was not passive, it was active, powering objects that reshaped the primordial gas, ionized the early intergalactic medium, and seeded the supermassive black holes that now anchor every large galaxy. And once you accept that dark matter might not just sculpt the universe gravitationally, but might actively participate in cosmic evolution by powering the first stars, you realize how little we understand about the substance that makes up most of reality. Dark matter is not just invisible scaffolding. It might be fuel, energy, the power source that ignited the first lights in an otherwise dark universe. How many other processes involve dark matter that we have not yet discovered? How many times has dark matter shaped cosmic evolution in ways we attribute to ordinary matter simply because we cannot see its influence? And once you realize that the universe's timeline might begin not with hydrogen fusion but with dark matter annihilation, you start to understand that the story we tell about cosmic origins is incomplete. The first chapter has not been written, because we are only now learning to see the objects that wrote it. Subscribe to Universe Uncovered, because the first stars were not stars, and the universe's first light came from darkness itself.